Welcome back to Math 104. In a randomly selected family with 7 children, what is the probability that the difference between the number of boys and the number of girls is at most 2? As always, for experiments of this type, we write down the appropriate row of Pascal's triangle, in this case the 7th row, because there are 7 stages in our experiment. The event we need to understand here requires a little bit more thought than some of the other events we've looked at. Just to fix a convention, let's say that this 1 is counting the number of outcomes with no girls and 7 boys. This 7 is counting the number of outcomes with 1 girl and 6 boys, and so on. 2 girls, 3 girls, 4 girls, 5 girls, 6 girls, 7 girls, which means with 2 girls there must be 5 boys, with 3 girls 4 boys, with 4 girls 3 boys, with 5 girls 2 boys, with 6 girls 1 boy, and with 7 girls 0 boys. We have a number of outcomes here where the difference between the number of boys and girls is less than or equal to 2. Here also we have a number of outcomes in which the number of boys and girls differ by a number less than or equal to 2. But for all the rest, the difference is 3 or greater. Here also the difference is 3 or greater. That means that the outcomes in our event are only these 70 outcomes. The probability of our event, therefore, equals 70 out of 128. Let's gather up some key facts about Pascal's triangle. For experiments whose outcomes can be described as words in a 2-letter alphabet, every entry of Pascal's triangle has a concrete meaning. It is counting the number of outcomes in a certain event. Whatever positive integer n is, row n pertains to words of length n in a 2-letter alphabet. For example, row 7 pertains to words of length 7 in a 2-letter alphabet. These numbers are counting how many words there are of each type. We have notation for each address in Pascal's triangle. N choose K, or written this way, N choose K. This notation is telling me to go look at a particular location in row n of Pascal's triangle. This 21 is 7 choose 5. I count up from entry 0, then 1, 2, 3, 4, 5. Each entry in row n, whatever positive integer n is, counts how many n-letter words have a certain number of r's and all the rest l's. This 21 counts how many 7-letter words there are with 5 r's and 2 l's. If you think about it, row n, whatever n is, row n has n plus 1 entries. So row 7 has 8 entries. Row 10 has 11 entries. Row 100 has 101 entries, because they go from entry 0 up through entry n, whatever n is. So in row 7, you've got entry 0, entry 1, entry 2, 3, 4, 5, 6, 7. If you count from 0 through 7, there are 8 spots there. The sum of the entries in row n equals 2 to the n. We saw that explicitly in row 7 earlier. This makes sense because the sum of the entries in row 7 should equal the total number of 7-letter words in a 2-letter alphabet. But that should also equal 2 to the 7th by the multiplication principle of counting, as we have seen earlier. We've also noticed that each row is symmetric about its center. We see it here in row 7, but we've seen it in every row that we've written out in Pascal's triangle. This makes sense. If you wrote down all the words, for example, that have 5 L's and 2 R's, and then you wrote down as a mirror image, so to speak, the corresponding words where there are 5 R's and 2 L's, you would see that for every word that looks like this with 5 L's and 2 R's, there is exactly one corresponding word with 5 R's and 2 L's. So just as these words can be mirror images of one another, the number of such words should be equal. Now here is a fantastic tie-in between Pascal's triangle and one of our favorite ideas from the course, that of an ideal data set. If you think about the experiment of flipping a fair coin n times however many n is, and you think about what an ideal data set looks like, and you organize the outcomes in the ideal data set by type as we've been doing, then lo and behold, row 7 is actually describing an ideal data set. If you flipped 128 times, and the results were perfectly representative of what will happen in the long term, then there will be one actual flip with all tails. There will be 35 actual flips with 4 heads and 3 tails. This is a very useful connection to make. Each entry in row n equals the sum of the 2 entries directly above it in row n-1. Row n-1 just means the row before row n. When n is 7, n-1 is 6. So each entry in row 7 is the sum of the 2 immediately above it in row 6, except for these 1s at the end, which are just always 1s at the end. We've seen that if all we're looking to do is find these numbers in the next row, then this rule instructs us how to generate that next row. But wait! Being able to explain this is important. If you wanted to take a math course that just involved plugging numbers into formulas, this is not that course. Before going on to the next video, explain why it is true that each entry in row n equals the sum of the 2 entries directly above it in row n-1. For purposes of giving this explanation, it's enough to explain in terms of the 21 in row 7. Why does this 21 in row 7 equal the sum of this 6 and that 15? Or why does this 21 equal the sum of that 15 and that 6? And it is not enough here to say, because the rule says that you just add them. There's a reason why it makes sense.